Hello, everybody. My name is Kevin Kotchak. I'm the founder CEO of Chemical Q Device. I'm here for this is discussion 101 for potential quantum radiomics machine learning workflows. So this picture that we have here is a very general picture. It's a bunch of different medical workflows. We're going to focus on radiomics in specific. And then you'll see here the Cirq.qsim is a simulator. It's available on different platforms. It gets you access to 90-core Xeon processor. And PennyLane has access to that too. And of course, GPU and multi-GPU support is going to be available as well. So this first slide of the presentation is basically, it's a little history of the technology. So back in the day, to detect cancer, especially skin cancer, Hippocrates, this is, BC, either by feeling or by visual observations. Now, this has since been enhanced to the discovery of the X-ray in 1895 with William Röntgen, and this is where he took the famous first X-ray of his wife's finger with the wedding band. And then later with that, chemotherapy helped to extend the lifespans of patients. And there's been a push to understand what's going on more inside the body. And then once we have those images, where radiomics shines is basically using AI or artificial intelligence with high computational, processing to determine more of what's going on inside of or what's going on, relationships inside of an image of the patients. So this term, is basically this. Radiomics analysis relies on AI algorithms, which can improve the accuracy of predictive models. And it was introduced by Lambin et al. In 2012. With the following description, automated extraction of a large number of quantitative features from medical images for characterization of underlying pathologies invisible to the naked eye. So you could have the best radiologists in the world, and number one, it would take too long to do a lot of images, even if they understand images very well. But we're talking about huge data sets with patient images over the course of many years and tying that in with advanced computing technologies to get better diagnosis based off that. So prognostication, disease monitoring, especially cancer. So you'll see a lot, tumor, cancer, oncological, radiomics in specific. And machine learning and deep learning algorithms are used. So some say, for instance, you can get away with using machine learning, but other cases, like towards the end of the classifications, those types of things, you're more talking deep learning in specific. And then these workflows are, it's basically, instead of just having like a stockpile of images, what everybody wants to happen is have a larger stockpile of images everybody can train off of. And then you're not just looking at it like eyeballing, for different types of diseases in these cases. So image acquisition and automated segmentation with deep learning neural networks. And then where quantum comes in is prospective better performance. So when you're talking quantum physics and quantum algorithms and data sets and these types, is that you're talking about a new utility, a new way of processing patient data that's never been established before. And, so there's multiple ways of going about that. But the most promising right now in workflows, because of a number of reasons I put, previously I published on the site, is basically these quantum simulators are the only tangible option right now for, you can get exact values right away, differentiation is similar to, classical machine learning, and there's no noise, so that it's just easier to evaluate. So you'll see these articles by NVIDIA and Brookhaven, very promising what the studies, NVIDIA over 700 GPUs, Brookhaven over 200, and it's in conjunction with other institutes as well. So here's what we have going on here. So this is a radiomics workflow. So this top row, starting with clinical data, going to image acquisition. So this is what we're familiar with. You have an MRI, you get an image, and then in these stages, you're talking reconstruction algorithms, pre-processing to remove artifacts and motion blurring and these types of things. And then image segmentation is, a little bit more advanced, but the bottom row especially is what's considered radiomics in specific, because this top row, we already have FDA approvals for reconstruction algorithms and segmentation algorithms. And, there's over, say about 15, I think, for one and over 20 for the other. So these are established fields. Now, the things that makes, radiomics, so powerful is that, the amount of data that radiologists want to train off of. And then, the amount of compute power that's also involved in this number 5. So feature extraction, so you get different types of features, histograms, textural shape, deep features, and there's tables of this type of information. That is what basically pinpointing exactly what a disease would look like in an image of somebody with this type of meningioma tumor. So that's what's coming out of here. And feature selection is similar. So, this is the meat of radiomics, where the top row is mostly established, and then you have these advanced techniques to more closely look at images, because we have the compute, and then we've gotten smart enough to start to build up these previous images as well. And then you have a predictive model, then performance evaluation, and you're using Python, PyRadiomics a lot of times with this. Are there any questions at this point? So you could feel free to raise your hand. You could also put into the chat as well. So this is really where the rubber meets the road with medical and quantum. So regarding this, so I'm going to refer back to these numbers. So this 1 through 8, as far as what's going on with quantum and what could be inserted with it. So if you've heard of generative adversarial networks, it's all the buzz. Can you use GANs is the short form term for it? Can you use that with medical data? In my opinion, you should use it for research and development purposes, because it's basically artificial data. So say if you have 10%, real images and 90% is noise, and the 90% over the course of this, adversarial network turns into other images too. Why not use that to, further the field through R&D? Although, it's still, I don't believe it's, fully passed where you can just, generate, medical images, off the spot. But it's what gives it's what gives neural networks, deep learning, the power is if you have a sufficient number of medical images available. So that's the whole use case. Would it be for quantum too? So in quantum, we're using, see where it says generator. These are circuits. So Q1 through Q4. So this is 5 qubits in specific. And then discriminator is a 3-qubit circuit there too. And these are not set in stone. And a lot of these are, they're not fully robust models. It's more to prove the point that you can have a generator and discriminator for quantum, as something that, may either give performance or give utility. Direct speedups, probably not the case, but if it's a case where you have a quantum algorithm that's, useful to use, with quantum simulators, and it's not available classically, then that may give an indirect speed up. But as a rule of thumb, pretty much speed ups, if you're simulating it with bits to make qubits, that's not an initial thing that you would find. So this is number 2. So there's a gentleman that was on this discussion. His name is Salvador Ivanegas Enrica, and he deals with this. So this is basically, so there's QualPhi, CQIR, NEQR, MCQI. So these are different ways of processing quantum data. So 3 of these are black and white, and then the 4th one here you can see is color. So, keep in mind with these types of things is that, these 1 through 8 that I'm going through are likely not all going to be direct replacements for classical. Over the course of time, probably not the case either. But there's certain ones of these that'll pop up, and this is done with quantum computing more so than quantum machine learning, that this might be a future standard, to work with is this, with quantum data and representation of quantum images. And then, so this 3 through 4 is basically, there's reconstruction, there's analysis with this. And basically this first section here is data acquisition. So these are like quantum sensors, ghost imaging, it's like the really nuts and bolts of how to acquire an algorithm with some form of quantum mechanics, either quantum computing, sometimes it's quantum machine learning. Now, the reconstruction algorithm on it, and I mentioned this before, we already have 15 of these. So 15 FDA reconstruction algorithm approvals for the brain, So, the same thing for the brain segmentation is there's 27 FDA brain segmentation approvals. So that's the part of the radiomics workflow, this top row that I showed previously, that's pretty well worked out, right? And, it's just taking it to the next level of, these huge data sets and more compute power to get, it's basically dimension reduction through feature selection and feature extraction. Are there any questions at this point? So this is 1 through 4. And I saw some new people come on as well. Feel free to put it in the chat, and you can also come on, or you can also raise your hand as well. And then this is basically the meat and the potatoes of radiomics in the form of quantum. And as you can see, these models aren't huge yet because most of them haven't seen, GPUs and multi-GPUs to get these, significantly larger circuits for prospective better benefits. But this top one is basically QFE layers and a classical classifier. So at the end here, this should look familiar if you're familiar with neural networks, the perceptron model there. And then these two previous, the two QFE layers, quantum feature extraction layers, are represented in quantum circuit form. So, you can take any classical algorithm and turn it into quantum, but and this is where the fields will, the areas that's under quantum, machine learning research will get more defined as far as like, when does it make sense to do something, with quantum physics with your data set. And likewise, this bottom one, and you can see this is a smaller model, quantum feature selection method. So it's kind of putting everything on the paper. And there's been a number of people kind of paving the way throughout this process. So this is, in radiomics as it sits today, a quantum, so feature extraction and feature selection with, HPCs and, GPUs, multi-GPUs is what's giving it the power over previous methods, not referred to as radiomics before 2012. Okay, so having a good quantum equivalence is really crucial to say, like, there's a better understanding of quantum physics with data sets. So these types of things just kind of if they as they happen. So in figure 7 here is basically these predictive models and performance evaluations for quantum. There's a number of different, I've run all these demos, actually all of PennyLane's QML demos at that time. And what I noticed is there's quantum kernel methods, which is an analogous to classical kernel methods. And there's a certain thing called address quantum circuits at the end of a circuit. So after the deep learning neural network and then right before the final classification. And I was pointed to this model by PennyLane researchers, the QVC model, and this is by Maria Schald at Xanadu. And, as far as having the most quantum potential for the future. So, as we get more, deeper circuits with simulators and, more qubits and these types of things. And I was actually able to improve this model with a simple modification in a different discussion. Now, those of you on the, fast track are aware of these transformer models. So you can have vision transformer, which is for images. You can have BERT models, which is for text. And then in this case, this is showing a vision transformer. In this specific site, it's a GitHub of a researcher at Hugging Face. Basically says that all of these are available and they're in some form of torch, or PyTorch. Now in Qiskit and PennyLane, you can use torch connector or torch layer to start inserting your quantum algorithms in these layers, just like how they sit in a torch, your superclass, and then define forward function, your forward pass, these types of things. So to me, that's where a lot of the innovation will happen. Now, with all of these things, you have to keep in mind of like how much theoretical performance you could have. So, let me work through the first three first, and we'll get back to four. So in specific, there's reconstruction algorithms out there for quantum. They're stored in quantum states, and when the data has to be input as quantum states, meaning quantum images, basically. So that's an option there too. That's an option for reconstruction, for quantum. A potential FDA upcoming submission, for instance. Now, number two, quantum-inspired neural architecture searches for segmentation. So this is using quantum-inspired methods in order to find, I believe in this case, it's better classical methods. So this gives you an idea of the broad breadth, of research that's going on. And this 3.1 is basically finding, quantum substitutes for existing ML methods. So say, for instance, like, in certain of these, like I said, you can get away with just using machine learning. You don't need deep learning. If it's doing certain things to the pixels, and it's just, you tend to get better, efficiency by using these smaller machine learning models before you go to deep learning. And then, the ones, say towards the end with classification, you would switch to something like the quantum deep learning or classical deep learning. Now, getting back to four is that although many working models exist, better performance and new utilities are needed. And in this case, if you're looking at the sheer number of parameters, if you're running like a 4-qubit circuit with 4 layers, that's 4 times 4, so you get 16 parameters, and that's with a 2 million parameter deep learning neural network, something like that, right? And they go up to billions, by the way. So the question is, like, is that enough, like just with that model that we have today, or is a new approach needed, greater insight into how these quantum circuits interact with larger data sets? And I know people want this to happen because there's recent studies that focus on contextuality, meaning that you change the quantum algorithm based on the data set that you have. So I've never heard of, well, I guess that happens in classical, but it's not. That's the first time I've heard, for an exclusive use for quantum circuits. So in steps 1 through 9, as I said before, and actually I think it's 1 through 8, as I said before, it's specific to, whichever one will come out first, what makes sense, because essentially there shouldn't be much regulatory, for a quantum simulator, because it's essentially running classical bits and it's doing quantum mechanics with some, math, behind that. Now, to get to the next levels, so, it's important not to just keep using the 2012 parameterized quantum circuit over and over again for new models. So say, for instance, I can do Hugging Face vision transformer, 2 million parameters, and I could do other hybrid models, other torch, deep learning, convolutional neural nets. But it seems to me, and I've run probably several hundred algorithms at this point, is that the core parameterized quantum circuit that's affecting quantum machine learning, because these parameters or the rotations of the gates are optimized over the course of the run, is not sufficient. And I haven't found anything where you can run, say several hundreds or several thousands of parameters at this point, and for that to be productive. So I think that's really key, right? Like we as an industry, we won't go too much further unless we modify and improve and have some type of understanding how we have larger data sets, quantum inspired is working. It's just the performance versus classical is typically not, much better. So, and there was also a post today by Wall Street Journal, and it was Jack Hidary had this quote. Basically, we're using quantum equations, quantum software on GPUs, right? So this whole push for, quantum computers is good, and we will likely have some use for big problems for quantum computers, but it's looking like for this quantum machine learning workflows, they call it QIML, is basically the simulators is going to be the way to go in the near term. And then, just to wrap this up, is that this is a huge industry. So if you took all of the world's data, 30% of it is healthcare. And it's growing at a compound annual growth rate of 36% through 2025. This is by RBC Capital. Now, imaging data accounts for 90% of healthcare data, so by volume. So medical images is 9 out of every 10 by volume, of healthcare data. It takes up a lot of room. So, and we're talking like, sometimes gigabytes and, these types of things. 5.5 billion global medical imaging procedures per year. Now, the global AI medical imaging field, so this consists of like, so you have AWS, HealthLake, you have Google, their suite for medical imaging AI, and then you have Nuance, which is Microsoft. So this, 45.6% compounding annual growth rate through 2027. So this is where the lines are kind of not exactly clear because, number one, well, brain or neurology has the dominating share of that, but global radiomics, 16.2%. And I believe this, they refer to radiomics as radiomics workflow. So in that case, that's everywhere from acquiring the image to the clinical data, reconstruction algorithm segmentation. And then, where radiomics is typically, known to shine is basically feature extraction, feature selection, and dimension reduction. So regardless, there's many opportunities for quantum, whether it's that first row of that slide that I showed you, or whether it's the second row, which is more like the advanced CPU or, CPUs, GPUs for feature extraction as well. So here's the references. So if you need to refer back to anything, so there's 95 right there. And I saw we had some people also join as well. And I wanted to open up. Does anybody have any questions about a specific slide that they'd like to go back to? And, like I said, feel free to put in the chat. You can also raise your hand as well. So, it's interesting for me because it really broke down as far as what in specific radiomics is referring to, as opposed to just, medical image analysis and these types of terms. Anybody else besides Gabe or besides Abe? And then, let's see here. So so for those coming a little later, this is what I kept referring back to, whereas this first row is more FDA approved with reconstruction algorithms, with segmentation algorithms. And then the second row here is more of like the advanced radiomics features. So this is the part that's is still not 100% approved as far as, what data set should we base off all of this? And then what level of control, which it's giving a lot of control to the computer, these classical computers, how it sits today with these features, what is being deduced from raw images, basically, that the computer's doing. So number 5 here. Okay, so yes, the slides will be up and this discussion will be up as well. Any other questions regarding any of the other slides, either the health or the quantum aspect of it? Okay, so, basically it's, it's an exciting field for sure. And then so those that research in quantum, know what I'm talking about. These are the models that we have in quantum are typically not huge models. Sometimes they're referred to as toy, but, the inner framework or typically researchers have found a way to do it in a quantum way. Now, the next step is basically, not only can you prove it's better than many other different quantum algorithms, which is fun and exciting, but it's typically hard to go to that next step versus classical, get that better quantum performance, maybe even an order of a magnitude, right? For people to switch to quantum, you have to incorporate another step. So, where would it make sense? Is it going to be the quantum GANs? Or is it going to be, feature extraction, feature selection, those types of things? And I'm also interested kind of where people are coming from as well. I think that we have some people that have returned from before. And, as far as like, the medical end with emerging tech and, definitely radiomics is emerging and it has for over 10 years, 2012, it said. So, it would make sense to make the industry aware of these developments in quantum right now, just as a heads up. I don't think anybody has something as far as like a direct replacement as of, September 21st. Awesome. So we had somebody comment here. So really keen to know the quantum aspects of the other than the ML incorporations, which is already there. What is the difference quantum is making here? So it just depends. It just depends on the step. So my understanding of quantum image processing, which is more, reconstruction algorithm type of field, that's more just quantum computing. So you're just using, you're not necessarily needing to have a training set in order for this unseen data. So I could be wrong, but that's how that seems. And a lot of the other ones, it makes sense in investigations to start off with a very simple machine learning algorithms. So you have support vector machine. I had mentioned random forest. There's quantum equivalents for most of these. So principal component analysis, there's qPCA. So there's quantum ways of doing machine learning on the simple end, as with classical, already is doing. So there's less liability with some of the smaller machine learning algorithms that are proven, to work well in the earlier stages of, true radiomics. It's just, you only jump up to deep learning when you have to, right? So if you need to know, glioma over the course of 10,000 images, these types of things, that's a deep learning task because you have to train that part before, seeing this unseen data to make it for the computer to make a conclusion about it. So it just depends. But typically that's the case, is you always start off simple. And, as radiomics sits right now, there's a fair number of just simple machine learning techniques, not deep learning, and then you work your way up to deep learning, or, in this case, potential quantum deep learning. Awesome. So Javier had a question. So you mentioned that there is a large volume of medical data, and this data you referred to is only from the, or is it? So it just depends. So the problem with medical data as a whole is that institutions, organizations, or universities like to silo it. So siloing means that it's not shared with any other university. So there's issues involved when you open things up, and I didn't include federated learning or quantum federated learning in this study, but there's issues that open up, with like, can we trust every single image from this specific, place, and those types of things. So, and I don't think it's patient identification that's easy to remove. De-identifying images shouldn't be the issue. So, it's usually that whole process of saying like, okay, everybody's on board, we have this big data set. And this is where GANs could come in, but you can't use GANs, as far as I know, to generate medical images to boost it up. So yeah, I mean, there's a fair amount of research. I read a paper in whole for this talk, and then previously in previous discussions, I read up on it too. So, as far as the, percent, if it's international, or, it's just really like, kind of the bigger institutes maybe at first coming together and, sharing the previously acquired patient images is what the question was asked. And there's, the LANI, so laboratory neuroimages. They have ADNI, which is for Alzheimer's. They're, they have these, it's multimodal data. So even the slide I showed you with the clinical data, that's considered multimodal now, where you have, EHR data, proteomics, genomics. Now you have radiomics, or images now, and you can consider all of these together. So, in the LANI studies, if you go to just, I'd get Google Kaggle, like anywhere up to 44 classes of brain tumors. And then I asked LANI, without being 100% aware of the purpose of all this. And I get all of this other data, that's, it's not going to be patient name and these types of things, but, additional things that can help with diagnosis beyond just images. And that that area or industry is called multimodal data. So yeah, that's going to be growing up with radiomics too, and explainable AI and these sorts of things too. So Abe asked a question. So what about technology going beyond the traditional tools for radiomics? Yeah, so I touched on some of these as far as going beyond the traditional tools. The ones most associated with radiomics, again, is feature extraction, feature selection. And this is basically, it's called dimension reduction. And it's taking only the pertinent information that's relevant to that case of cancer or whatever that the computer knows. So that's that task right there, is doing it with quantum circuits, and a lot of times it will be hybrid networks. So on one of those that I showed you for for feature extraction, I believe it also had a neural network on the right side of it. So there's a lot of creativity that can go behind putting quantum circuits at different parts of neural networks and models and these types of things. But at the end of the day, like I said, either having a restricted number of quantum parameters that we have now, or having an update to PQC model, which was made for noisy quantum computers. So there has to be something better as far as data set understanding in quantum circuits. Okay, so the other part of the question, such as security. So yeah, I included a fair number of so this is like patient security kind of stuff. There's a company called Sandbox.aq, and then so they're Google spinoff, and basically what they do is, there's another company called QSecure, and between those two, they'll take the NIST. They're called post-quantum cryptography algorithms. It's that PQC, and they're classical algorithms, but they can defend against quantum attack. So for patient security, at least Sandbox.aq and Mount Sinai Health System have already started going down that route. So yeah, and the last part of the question, any thoughts on the future of that? Do you foresee its development? So QSecure, Sandbox.aq, and other types of companies like that, it's basically the application of it all. Just like in quantum algorithms, you can't we've been making quantum algorithms since the 90s, and there's a big table of quantum artificial intelligence and the 4 different types of quantum algorithms. The issue is the application. So just like in cybersecurity and other fields too, is how can we apply those NIST algorithms in a broad range of applications? The Google Chrome browser, I think, now initiates one of those NIST algorithms in the browser. So if you were asked to upgrade the Chrome browser, I think that was the case there. So the practical cases, so that's a practical case because it's a classical algorithm. It runs on any, I think most, if not all, classical computers, defending against a quantum attack. Now, what makes quantum-inspired machine learning practical is it's running on CPUs and GPUs, quantum mechanics, quantum physics, and it behaves in a very similar way to existing machine learning. So for instance, there's an adjoint differentiation method that is similar to backpropagation, which is a trademark, a staple in deep learning. But in this case, it's also including the quantum circuit. So it's reverse accumulation, through classical and quantum layers. So if you can get that to work in some model, there's a fair number of models you can get that to work. Anyways, so yes, there's other advantages. This practical advantage of quantum-inspired machine learning has not hit yet fully to the real quantum hardware. So that's why there was another talk by, not QSecure, this company up in the Bay Area. So QCware. So they have these events, and they specifically highlighted quantum-inspired machine learning in one of their demos, because it's like, machine learning, everybody wants that, and it's supposed to be the primary application for quantum computing. So, should be looked at. Any other questions? Anything? Anybody that we haven't heard from so far? I mean, in literature, you usually find what you're looking for. If you're looking for cybersecurity, finance, transportation, right? It's like climbing a mountain. It's like figure it's climbed. It's just we're not there yet because simulators will get better and real hardware for the, big, probably non-machine learning problems, like as far as workflows, that'll be that application. And then there was a poll this week. I shared this. So, and I've kind of touched on some of these. So I'm going to include the poll, and it's pretty much, it just had like a day or two, maybe 2 days left. So this is on the, share the results here. Poll 1. Okay, so that should be that. So I'll open it up with you. And the question is, what would you like to learn most about regarding quantum machine learning workflows? So this is very pertinent. So the first one, which was the winner, is pure states. So if anybody has any questions, regarding these, but pure states is basically when you don't have quantum noise, and when you can map over the surface of the quantum bit instead of inside of the sphere. Now, these are represented by ket notation as opposed to density matrices if you have quantum noise. So are there any questions regarding pure states? And again, I put this in the chat there, the results. So the second one, which was a tie for the third one, is the adjoint differentiation, which I was talking about. Okay. And so, for instance, for adjoint differentiation, there's other types of, there's the parameter shift rule, which you typically use for hardware. With adjoint differentiation, it's very similar to backpropagation in classical machine learning. So in this case, the quantum circuit, like it's like memory efficient, and the whole process is basically like what backpropagation is. So Rob, you put in the chat too, integration into generative AI, and then we'll get to that. So we'll finish the poll, and as you can see, exact expectations 32%. So for anybody that's run, Qiskit hardware or Rigetti or Google, quantum AI, these types of hardware, INQ, is that you're dealing with probabilities. I don't think there's a way to get exact expectation values right away. And in the PennyLane documentation, which they're kind of like leading this charge with, quantum inspired artificial intelligence, they said that, if you have a Hadamard gate and, basically the known solution is 0, that's the exact output. In order to run, say if it's like 10, 100,000 shots, something like that, is that your eventual probability, it never gets to 0. So when using this type of, the languages, I don't know if PennyLane is the only one that does it. So if you have if you have machine learning and you have a mini batch, so say there's 10 mini batches to your whole batch of 100, then that means the quantum algorithm has to be ran 10 times, in order for that first epoch. So epoch is a basically the first kind of like run for machine learning up to trying to get better accuracy. So if you can do exact expectation values with that, is that you don't have to say for every single mini batch, you don't have to run 10 probabilities, and that n probability is not the exact value. So I don't know if this is run up front. So say like right when you do the quantum circuit, the software can figure out what the answer is. But it'll likely, move into other types of technologies, quantum technologies too. So those three combined is what I put in the chat here. You see with the 22 votes. And, you know, they're principles to quantum inspired machine learning. So this is the one that, you know, the Bay Area company, not QSecure, QCware, you know, they had this presentation on. They said you can do this today, and I do this today. It's just the accuracy have to get better, and you could probably find some quantum algorithm that has a new utility today compared to classical, even if things aren't like, you know, fully worked out with, you know, how our understanding with qubits and data sets. That would be a good thing to do to research. Because there are quantum algorithms that you can't do classically. So a new application, a new utility, that would make sense. So and then, you know, Ravi got into generative AI. So I don't go too much further than, you know, GANs with that. So generative adversarial networks. So was there anything else, Ravi, in specific that you had with generative AI? Yeah, and you know, this ties into, you know, natural language processing, Chat GPT, OpenAI. I think there was a new DALL-E. It's DALL-E, and then I typed in is basically to connect it to DALL-E. I said a quantum computer on my desk, and it produced an output of what that would look on based on other images that it's seen with quantum computers. Yeah, yeah. Okay, so. Yeah, and I'm sure there's a lot of study with it, and I'm assuming that you mean classical research initially, you know, classical generative AI with brain imaging, and then also the you know, the quantum version too. Now, Abe put it in the chat. QCware does much of the software work for JP Morgan's quantum finance innovation research initiatives. That makes sense. So yeah, there's, you know, definitely some leading organizations with all of this. And I remember there was a multiverse computing. They're based in, I think, Spain. And they said that there's an algorithm that can do 100 times speed up. And today we're just like, yeah, we have lots of exponential speed up algorithms. However, the trickier part is incorporating them in a model. If you have classical data, you could lose it. You could lose your speed up right there in embedding that classical data into quantum. And also with the outputting the quantum states into binary. Those two processes, they're like the IO problem described by Seth Lloyd at MIT. They affect speedups. So many people, when they think of quantum advantage, they think speed. But like I said, the issue is like, you know, with a lot of these models that are functional, is that you have to convert classical into quantum and then quantum back to classical, you know, through embedding, variational layer, and measurement. And that process is can take away the speed of an exponential speed up algorithm. So that's where I say, you know, as far as new utility, look at a way that, you know, classical's never could be used on data sets, and now you're using quantum for it. That's new utility, and that can be done with, you know, simulators and you know, the Cirq.qsim. There, I did a benchmarking study this week, and it basically showed that the single CPUs were like significantly slower. I think 5x, like 20 seconds compared to 130 seconds, something like that. And I wasn't able to activate Cirq.qsim's 90 core Xeon processor, I don't think, because I got the same results as a known single quantum bit for basically PennyLane's Lightning.qbit. So yeah, if you can get CPUs too that you do multi-threading and across many CPU cores, you could also do that, right? So I ran the Lightning.gpu for the first time, my first GPU quantum simulator on Colab, because I selected a, you know, like a V100 or A100 GPU. So it allowed that simulator to work. So, you know, just keep that in mind. A lot of times, like the most powerful technique. A lot of times I'll be on the V100, NVIDIA V100 GPU. And, I'll switch to the A100 like at the end, just because it's like $1.30 an hour versus like 50 cents for the V100. Okay, so Javier has a question. Can you provide us with the reference of the problem of changing the information from class? Yeah, so I did a study on this. Let's see. I'll put the 100 research. So just because of these other things going on my desktop, you'll be able to get to this. So it's 100. If you search for embedding in that PDF, that should pull it up. And basically, if you can have pure quantum data that you don't have to convert before it goes into the variational algorithm for training and quantum machine learning, is that saves a lot in terms of time, CPU costs, these types of things. So a lot of times if you have an embedding layer, like on Qiskit, there's like Z feature map and ZZ feature map, but these are like sometimes too big, right? Z is like 4 layers wide, and the ZZ has entanglement and it's like multi-layers wide. So it's not always that you need a huge embedding layer. So that will help to, keep the circuit size down and the speed up. So yeah, I put in the chat the 100 resources for that one. And, like I said, I also did a healthcare quantum algorithms, which is based on, there's certain, so a state vector algorithm is typically, if you increase the number of qubits, it goes up exponential in RAM and exponential in runtime. So that's like a big, you don't really want that. So if you can do things a different way, so, instead of entangling in just single qubit gates, but usually that path towards full entanglement in your quantum circuits, you're going to encounter, we call them barren landscapes or barren plateaus, whereas in the other ones, not as much. And you can do tensor networks. So there's tensor networks for, CPUs, GPUs, which can help get the qubits up, but you can't do as much entanglement traditionally. So yeah, there's a number of different approaches that you can take. And like I said, with this specific talk of these, 8 big points, is that the ones that will come over from quantum are the ones that say like maybe an order of magnitude better in a specific metric. Then it makes sense to run a quantum simulator. And, it's forecasted that the CPUs and GPUs can't catch up, just on their own, without doing a, quantum mechanics, with a simulator. So there's, if quantum machine learning is the principal application for quantum computing, and everything in the news, especially with the Wall Street Journal today, are saying we're using, GPU quantum simulators. There's a Tom's Hardware article that said that GPU, quantum simulators will lead real quantum computers for a while. And I see real quantum hardware having applications, but just for big problems, unless there's a significant overhaul with the, differentiation methods and, there is no quantum noise, right? Like even if you have a little bit of quantum noise, I believe you have to switch from, pure state to mixed states or density matrix, where more complex math and, computational cost. And then anybody that we haven't heard from? And there's no short of quantum resources, that's for sure. So, basically any question that you have is probably valid. There's Qiskit Slack. I'll just put the names of things in the chat. And then the PennyLane, or it's actually called Xanadu, parent company. Xanadu discussion are 2 big ones. And the Qiskit's starting to get busier with the AI machine learning, as it should, right? So you can do a fair amount on Qiskit with machine learning, with their torch connector, like PennyLane calls it torch layer. So if you're familiar with programming neural networks in PyTorch, how you have like self dot whatever or x dot whatever, you know, in the forward pass, is now you can start incorporating these layers, but they're Python functions. They've already been figured out what happened with the quantum circuit. So now it's inserting these things as they're special Python functions. They act like any other Python functions. So some things aren't as complex as what people imagine them to be. It's just, you know, you have to go through the 3 or 4 steps before that to define the layer, you know, what you want it to be. And there's 2 demos I included in this presentation here too. So I definitely do the demos too. So I've done all the PennyLane, their machine learning ones, and there's a fair number of the Qiskit ones too. Any other questions? So feel free to come on too. You know, everybody's started in quantum at some point. If you're advanced in quantum, that's good too. I would just say, you know, just get the hours in, right? So if you really want to know quantum and you're working another job in data science, you know, you'll have to put in the hours for quantum, you know, at nights or on the weekends. So it just doesn't come, you know, right away. And I wish I could just funnel down and give like what you absolutely need to know, but that's part of the process too, is you finding out, you know, what you think is most important to study in quantum. Yeah, and I would start, and so for Abe and others too, you know, start off with quantum circuits. So those are the algorithms. Now what's inside of them are called gates. So they're single qubit gates and 2 qubit gates and 3 qubit gates. The most common are single and 2. So a single qubit gate, you can have a rotational gate, an X, Y, or Z that doesn't have trainable parameters. So meaning it just, you know, turns the qubit 180 degrees over that specific axis. And then the next step up are called trainable single qubit gates. So these are rotational gates, but we call these RY, RX, and RZ. And then in these cases, these have parameters that you can train or you can't train. If you have embeddings, you typically don't train them. If you have variational layers, like this middle chunk, this algorithm, then it's just like deep learning. So the rotations of the angle of all the different parameters. So if you have like, you know, 4x4 circuit, 4, you know, qubits, 4 layers deep, is that all of those get optimized in a certain way using optimizer functions hybridly, just like classical, by the way. And they'll turn a certain way. So, you know, it's trying to get the best accuracy, just like machine learning. So if you know machine learning, these principles carry right over. And then 2 qubit gates are like entangling. So you can have a CZ, you can have a C naught. C naught is probably the most common. Both of these are a control gate with an X gate or a Z gate, and they're not trainable. So they don't contribute to artificial intelligence. They're just in the circuit. So, you know, you'll see a CX gate. I think Qiskit calls it CX. PennyLane calls it C naught. I think Cirq, so Google Cirq is C naught. So the very first step, you know, learn those, take the tutorials on quantum gates and quantum circuits. And you can't avoid them. They'll be in every single model. Like if it has a quantum algorithm, unless, you know, dealing with non-negate model, like pulse model, but, you know, huge leg up. And if you have an intuition over one gate or another, change it and see how it operates. So Qiskit has certificates and PennyLane has tons of demos. So last I count, probably over 100 for PennyLane demos. There's like, I think 27 quantum machine learning ones for PennyLane. So, but yeah, just, you know, get involved with the community. That's like, it's just like with any other field. Like you really have to get your time in. Okay, so Abe had mentioned, so programming for optics imaging on high energy physics. Yeah, so, right. So there's multiple different ways to, I've seen incorporating machine learning into quantum sensors, right? Like classical. So you don't always have to have like these, strict rules of like, the quantum algorithm has to be like this and like that. There's many different ways you could use them. So my comparison between variational, quantum classifiers to address quantum circuits or quantum kernel methods, it seems like you might get more advantage out of the quantum classifiers. So sometimes the research will save you time up front, so you don't get down a path in quantum that we've found out, you probably won't get much. Like mathematically, how the data sets behave with the qubits, those types of things. So yeah, and Dino, if you want to come on, you can. So yeah, Dino says he took this course last year. I'm not familiar with qubit.org, so maybe you could put it in the chat, a little bit more. There's edX, so I'll put in two good edXs. So one's Linux Foundation, so it's good to see Linux is involved. So I think it's edX.com. No, and these two, one of them is like that. It's like circuits and gates, right? So if you forget one, that's understandable. But most circuits just use CXs and RX, RY, RZs, CZs, sometimes Toffoli. And I'll give you a hint at this point where we are with quantum circuits and our understanding of data sets with quantum circuits, you're probably better with smaller quantum algorithms. So the deep learning network, classically does its thing, and then say a 4-qubit, 2-qubit, sometimes make it, more layers if it was 4, which means, deeper. So that's the thing right now. My best algorithm right now is very simple, and it's faster than the other ones from literature. I mean, most literature, and the best performance across different data sets too. So keep in mind you're dealing with the surface of a sphere, which is called the Bloch sphere, BLOCH, which represents the quantum bit or the qubit. So if you're dealing with pure states, and say the surface area of the sphere is represented as a mathematical equation, then it might behoove you to make quantum circuits that equal that mathematical equation. Yeah, so this first one is Linux. Linux Foundation. So yeah, this one's called Quantum Introduction to Quantum Circuits. So I'll put this in the chat here. Actually, that's a little big. And I recommend this to anybody. So it's not too long. You can audit it if you want. I don't know why the link is so huge. So I think I'm going to shorten this link here. Okay. So you don't get a certificate if you audit it. Auditing just means you're watching the videos. So you can log in as an account. They give you like, I don't know, like 60 or 90 days to complete the course. And then I'll just do it in like 2 or 3 days. So that's the Linux Foundation. I put that in there. So that's a good start for sure. Now, the other one is a lot more advanced, and it's a University of Toronto. So in this specific one, they have lectures. So if you believe in the theory of mirror neurons, where if you're trying to get a point in your career or your studies, just listen to people talk about the field that you want to master in, this would be yours if you're not at that level. So Seth Lloyd's in it, Matter Lab. I'm trying to think who else. Maria Schald is in that one. So she's at Xanadu PennyLane. And a lot of times they'll, either a lecture with some colored markers, but that's a good one too. And I'm kind of curious as far as, because I kind of caught a little bit as far as what people want to get into, generative AI for certain models. If you want to put it in the chat, the specific area of research for quantum computing or quantum machine learning, that would help. So I have another poll out that helps with this too. So this one's more like GPUs and cuQuantum and those types of things on my LinkedIn. So, but yeah, go ahead and put it in the chat so I can, address, like as far as what people want to get into. And, just an FYI is that, people do have PhDs and postdocs in computing or quantum machine learning, or some variation of those. Now, a lot of things, not in mine, because I've kind of converted into like application with quantum, is you want to be very careful of not, taking it anywhere, right? So once you learn the circuits and the gates, find a way to apply it, run demos. And, if they say, try this gate instead of this gate, substitute it, see what the performance is, right? So that's what I kind of, if Qiskit came out 6 years ago, right, 2017, something like that, and PennyLane was a year after that, the days will likely come where it's not just, introductory beginning, material week after week. So I guess the moral of the story is like, if you feel that motivation, to go further with QML or quantum, part of it is, like the amount of time you want to spend or set for spending and just doing it, because the field will go by, right? If everything's just basic and introductory, just every single week, it's just like we learned a new basic thing and new basic thing. And because there's been people that come on this discussion that they have degrees in quantum, so they understand the basics, right? So taking it to application, minimum viable products, those types of things is really important, right? So it's making up your mind. If you don't have enough information as far as why to make up your mind, there's 3 quantum hardware companies that IPO'd for over $1 billion. And, quantum machine learning is the primary application of quantum computing. There's, IBM installed a quantum computer at Cleveland Health Clinic in Ohio. And, NYU Langone and Fermilab are making brand new MRI analysis with quantum sensing and quantum computing. So Brookhaven, National Lab, over 200 GPUs, quantum simulators, these big experiments with quantum algorithms, basically. So yeah, you have to make up your mind. And a lot of times if it's financial, write it down and then, do the research about QML. There was a famous Los Alamos National Laboratory paper, and this is more technical, the challenges and opportunities of quantum machine learning. Now, it's in a Nature paper, scientific reports, but you can access it through Archive, ARXIV. So, but you read enough of these and you think, okay, there's people that have taken way more risk than you or I have. So, you can pull these things together technically and financially, and this makes sense for your career, those types of things. Awesome. So I saw another comment in the chat. Any other kind of questions or comments? Any we haven't heard from? I think we heard from everybody. So then we'll go to Javier here. Javier says, I'm interested in protein folding problem. So there's about 9 or 10 organizations that do this type of stuff. So ranging from, it's called Menton AI with 2 E's. There's Polaris QB, and the CEO has talked on this panel. There's Johnson Johnson. They're collaborating with another company with it. The issue is the limitations of simulators is the RAM required, and then also the speed, how long it would take with the. You can't really. You could use it with quantum annealers. People do. I know that's kind of a standard thing. But you're talking sections of like residues, like of the. I haven't kept up with this, but say like 7 or 10 residues. This is maybe a year ago, where there might be hundreds, thousands, millions, in the sequence that you can analyze with quantum techniques. And that's not bad, right? You want a working model. And if you change something and then it changes this, the results in a certain way, and you can prove your hypothesis, these things are valuable. Like I said, I don't think, unless you're doing like multi-node and multi-GPU quantum simulators, you could probably get up there. I would check it into that, how you're with the NVIDIA, it's called cuQuantum. So I'll put that in there. And I've only seen a limited number of these multi-node GPU experiments. I've done a single one. And like I said, with NVIDIA, they did tensor networks with like over 700 qubits for 700 GPUs for about 1,200 qubits. And I don't know how, deep that is. So how many layers, per qubit. So I would check that out. And I think it has a good chance as far as the, NVIDIA is the only one doing GPU quantum simulators. There should be more competition, but Wall Street Journal today focusing on the same exact thing. So, the Jack Hidary works at Sandbox AQ, which I mentioned. They do cybersecurity and other things too. So it's tangible, and there's several working parts that have to be in place to have a correct machine learning workflow, as opposed to like just doing a big problem, just on the quantum computer, then taking those results. So just 2 different applications there. So I would head toward that route. If you can get the Cirq.qsim, this is I'll put this one here. This is a 90-core Cirq.qsim, 90-core Xeon CPU. If you can get the 90 cores to fire up correctly, that'll save you a little bit of coding. And pretty much anytime you use a GPU quantum simulator, you have to pay for it. The Cirq.qsim is actually based on the quantum simulator from Quantum Advantage, the first Google Quantum Advantage. So it's not the supercomputer running Cirq.qsim. It's an advanced CPU, a Xeon processor, but nevertheless, it's free. So a lot of times you're doing screening, so you just need to be in that kind of that middle area, like say screen with Cirq.qsim if you can get more threads, and then switch over at the end to a V100 GPU, and then like an A100 type GPU for your final speeds. So keep that in mind too. And some platforms charge by month, and that can be hard to account for and when you're doing experiments, if you're not an expert in those types of monthly services. Awesome. Any other last questions or comments? And then I had put in the chat those links there. So for certificates, and keep in mind, like, you really don't want to just come back every single week in quantum. It's just like basic. It's just like, just in your mind, make up. I finished gates and circuits, these tutorials, I understand them good enough. I'm going to go on, right? So go on to models, demos. apply them, those types of things. So awesome. So yeah, this has been discussion 101. So this is September 21st, 2023. I'm Kevin Kawchak, founder, CEO of Chemical Q Device. Hopefully this has been helpful. I should have this up on LinkedIn pretty shortly here, the deck, and the discussion will be available on YouTube as well. Have a good rest of the night and have a productive rest of the week. Thanks, everybody. Bye.